Okay, today we have Ahmet Güloğlu from Bilkent University, Ankara, and he'll be talking about non-vanishing of L functions at the central point.
Okay. Thank you very much for the invitation and for pushing me to give a talk because I was getting lazy. Okay, thanks, İlhan Hoca. Um, so this few pages of the talk, you will be hearing my voice, but you will be listening from Google, the artificial intelligence Gemini. So he gave the answer to my question. So let's start. Let's see. Okay, here's the summary of what we're going to talk about. Um, L functions uh, are important, it says, as you can see, and the central point will be our main interest in this talk. And the main question will be, do these functions vanish at the central point s equals 1/2? And the quick answer to this question is yes, they do. But the main expectation is that most of them, they don't vanish. And that was the question that I asked Gemini, and he came up with a couple of pages for me. So vanishing is related to several things, as you can see here. Birch-Simons-Dye conjecture. For elliptic curves, if you get an L function and normalize it so that the center is at 1/2, then the rank of the elliptic curve for the rank of the rational points is given by the order of vanishing at 1/2, for example. And now there will be another result I will talk about later, hopefully, which relates the vanishing to Ziegler's. And then there's also other things which are important, like deformation theory and so on. As I told you, vanishing is expected to be rare within a given family, depending on what the family is, of course. So, and one of the main reasons why it is expected is because of the random matrix theory and the relation between the matrices and the zeros of L functions. Okay, we're going to talk about this later. And because of this, if you can establish an analogy between these two, then you can get some non-vanishing results, basically. Okay, and the tools that are used, I want to talk about today. One of them, at least two of these are here, which is one of them is using moments of L functions, and the other one is using uh, like distribution of zeros of L functions using Kac-Sarnak philosophy. Okay, here you see, for example, the second moment taken over a given family. All right. And most of the results, if you want to get a good result, in other words, you may have to use, most of the time people assume Riemann hypothesis already. There are some unconditional results, of course, but generally you need a Riemann hypothesis. And the results you're going to get will depend on the family that you choose. All right. So that's the end of the talk. So these topics, for those who are interested in, can be found in this book, the famous book by Ivan Ilyin Kowalski, which I call an encyclopedia, especially the last three chapters, 24, 25, 26 is the last chapter of this book. And 5 gives information about L functions in general, I think. 26 ends up with non-vanishing results. And 25 is about distribution of zeros of a certain L functions. Okay, that's by Google basically so far. So what I would like to do is I would like to introduce or just remind the audience what an L function looks like by starting from the Jesus of L functions, which is the Riemann zeta function, of course, the first L function. All right. So all the L functions basically resemble in terms of their properties the zeta function. So let's try to understand this one. This is given as the series, infinite series, and this is absolutely convergent in the half plane, real is greater than 1. And also, you can write this as an infinite product over prime numbers. This is also convergent in the same half plane. And once you plug in s equals 1 here, this is what we teach in calculus. You get the harmonic series. This is divergent. But if you want to ask the more general question in your calculus courses, for example, what happens when s equals 1, but the imaginary part is not 0, for example, is this convergent? You can ask your students. If you, I'm planning to do that, by the way. So is it still convergent at that point? You can ask. Okay, so what's the analytic continuation of this function? This is due to Riemann, of course, 1859, I think. He proved two results and made several conjectures. So he multiplies the zeta function by a gamma function and some factors here to form this completed L function. All right. Initially, the right-hand side is convergent for real s still greater than 1. But on the other hand, the left-hand side can be written as an integral, which converges everywhere. So this is an analytic entire function, analytic everywhere on the complex plane. And also, as you can see, the variable s appears only here. And if you plug in 1 minus s, you will see that it satisfies this functional equation. So the symmetry is around the axis s equals, real s equals 1/2. Okay, what you see, this is also more, this is also interesting in another aspect. As you can see that we have this theta function appearing here, which is given by this formula. So this z is a complex variable here. We have this function, and it satisfies these two transformations. And it turns out that this is, in fact, half integral weight modular form over a congruent subgroup. So I think the first time you see the relation, like maybe the beginning to the Langlands program here, you can see, for example, the relation between L functions and the corresponding automorphic forms here. These are related through this integral equation. So that's also important in that sense, I think. All right. So now you basically you define a zeta. You can, if you leave zeta here alone and take everything else to the denominator here, because gamma is never 0, it will have some poles. Zeta will become an entire function this way, except a pole at s equals 1, because of this integral representation. So that's the analytic continuation of zeta. So zeta is this guy left side over this one. All right. Then you look at the theory of entire functions from the complex analysis perspective, and you realize that this entire function has order 1. Therefore, it has a Hadamard factorization given by this. And you see there are so there are zeros of this function here. And when you look at the right-hand side, none of these guys are 0 except s equals 0 and s equals 1. Therefore, all the zeros of this guy should be coming from the zeros of zeta itself. Yeah, the zeros of zeta and psi are the same. The pole of gamma cancels the 0 here. Um, so so this way, you know that zeta, Riemann zeta function has infinite many zeros because this guy has infinite many zeros. And to understand where these zeros are located, you go back to the definition of zeta again. You look at this Euler product. Again, from complex analysis, this guy is never 0. Therefore, this sum is never 0. Otherwise, you wouldn't be able to show that this is not 0 for complex variables. Because this is not zero, and because of the functional equation, this guy over here is not zero to the right of one and to the left of zero. Therefore, the zeros should be between real s equals zero and zero, real s equals one. That's called the critical strip. So these are the non-trivial zeros of zeta function. These are called. So these zeros I'm talking about are the non-trivial zeros of zeta. There are also zeros of zeta coming from the poles of gamma on real s less than zero. These are called the trivial zeros. All right. So that's you can read all this information from here. Another thing you get directly from this relation here by taking the logarithmic derivative of both sides is this relation. This is leading us to the prime number theorem. Basically, this is almost saying that the weighted sum for the primes is asymptotic to x if you can show that the right-hand side is small. Okay, this is all because of this relation above. So that's one of the conclusion, one of the consequences you would get from this equation. Another consequence is as I told you, zeta is not zero for greater than one, and it is zero for real is less than zero only if gamma is has a pole, and we know where they are. And also zeta has infinitely many zeros in this region. Sigma refers to the real part of S. And furthermore, you can get one more information if you carefully look at this integral representation by bounding the theta function here. Trivially, you can show easily that zeta, in fact, is not zero. So we were talking about the non-vanishing of L functions. This guy is definitely not zero on the entire this part. Sigma equals zero. So I'm talking about this. Okay, the fact that zeta is not zero on the line sigma equals one is equivalent to the prime number theorem. Therefore, all the zeros are now in strictly in between 0 and 1. And finally, the Riemann hypothesis is that all non-trivial zeros we're talking about should lie on the line s equals 1/2. So that's the general story of L functions. They have a gamma, then they will have gamma factors. They are supposed to have Euler products, and now they can be complete with entire functions or maybe with some poles, and then they will have functional equations. So you'll get similar results for L functions in general. Okay. The next topic, I mean, if you want to go investigate further what the zeros look like, you can try to count them in a box in the critical strip up to a height t, and then Cem Hoca talked about this before, I think, and then you will get this asymptotic formula due to one from Mangold, which was conjectured by Riemann. Okay, so there are this many zeros, and in a box of size t, if you divide by t, you see that the zeros get close to each other as you move up in the y-axis. Okay, here's the result that people studied. What happens if you look at the zeros, again up to height t, but now you require that the real part of the zero should start from alpha and go up to 1. So, and alpha goes from 1/2 to 1. And one of the results, not the best result, but one of the earlier results is that the number of zeros in this region, in the smaller box, is given by this formula. And if you look at this part, alpha times 1 minus alpha, this is a parabola and it has a maximum at 1/2. If you plug in 1/2, you're going to get, you see that this will be a 1 here. But if alpha is to the right of 1/2, then this whole quantity will be less than 1. Therefore, if you compare it to the number of zeros t log t, this part is definitely a little of that size. That means most of the zeros should be near one half. It says automatically you get this result by this result. So it says almost all zeros should be near the critical line. This. All right. But the stronger result, which I want to mention, due to Selberg in 1942, which started with I think Hilbert and Littlewood, but then Selberg showed that there are t log more than t log t zeros on the real line s equals one half within a box of size t or 2t. And the reason I'm mentioning this is the first time Selberg used the modified the weights basically to get this result. I mean, previous people used it, but they couldn't get this good result. So I want to mention this a little bit. So what happens is that Selberg defines a function like this. Here's our zeta function, and this part is the completion of zeta by a gamma factor divided by its own length. So this part is never zero, basically, because of gamma function. This function is always greater than or equal to zero because of the absolute value. So if you can show that the left-hand side f of u, this entire function changes sign, then this part should be the one that's changing sign. And every time you change the sign, you know that this guy should be zero between these sign changes. So you will get, that's the idea basically. Try to count the sign changes. Try to find enough of them. And to be able to do that, the idea is this. So you look at these kind of integrals, and if you look at this one, as you can see, if these two things are the same, right, f of u is not changing sign basically. Otherwise, it is changing sign. So to be able to see sign changes, you compare, you look at the count, it basically count all the little t in this box for which this inequality holds. That's the idea. All right. But what I want to say again here is that this function plays the role of, in some sense, that this is the modifier, is this should act like 1 over zeta so that it will cancel the effect of zeta. That was the idea of Selberg. So he wrote this sum, and the coefficients he chose exactly as the square root of 1 over zeta, so that when you square it, it should act, I mean, kind of like 1 over zeta. That's the idea of modifiers. Basically, you want to get rid of the large values of this one by removing it with a modifier. Okay. Next, quickly, I want to mention the L functions. Uh, so you fix an integer, and then you look at the units modulo Q. This becomes an abelian group. You look at the homomorphisms, group homomorphisms into non-zero complex numbers. These are the Dirichlet characters. All right, and this group of characters is isomorphic to the group itself, the unit itself, of course. Now, for each alpha, for each character, you define an L function. This is also convergent for real s greater than 1, absolutely convergent, and then you have an Euler product. But the difference of this one, the zeta, this is also convergent, conditionally convergent in the region real s greater than 0. However, the Euler product itself is not absolutely convergent. So you cannot use the fact, so you cannot show basically from this Euler product that this guy is not going to be 0 at 1/2, for example. So you have to show that the sum is not equal to 0 when you plug in s equals 1/2. I don't know if you can show that. I guess nobody could so far. Um, okay, they have as I showed you before, and they have a gamma factor, and in front of them, you will see what's called the analytic conductor of this L function, Q here. And this is also an entire function as long as you have a nice character here. And then the difference between zeta function, as you can see, the functional equation relates chi and chi bar here. If the character is not complex, of course, this will be also chi if you have a real character, for example. And this number over here is always has absolute value 1. In fact, this has plus minus 1. So it's always 1. Okay. For a real character, this will be equal to 1. Sorry. But I think it's a good point to mention. So if you have a similar completed L function for a different L function, and then if this number over here that you see here is turns out to be minus 1, and this function and this character are the same, that means it's a self-dual function, then obviously because of the minus sign here, if you plug in 1/2 to both sides, you will see that the function vanishes at 1/2. So you can have an infinite sum of L functions which actually vanish at 1/2. Okay, that's what I meant by choosing the family correctly. So for some families, you can get 0 always. Okay, quickly, if we go back to the Riemann zeta function and plug in 1/2, uh, on one hand, you get zeta of 1/2 is equal to this guy divided by this factor. On the other hand, this is given by integral representation. You can, as I told you, by bounding this one, you can show that this expression is larger than 0. So zeta of 1/2 is not equal to 0. It's negative, in fact. But okay, also for this one, you can write 1/2 here, and then you will get this expression. But can you show that this is 0? If you can, please contact me as soon as possible. Okay. So this is an infinite sum, and I don't know how to show this. I don't know anyone who knows how to show this anything. Okay. So basically, how do you find the value of L function at 1/2? If these integral representations don't work or these kind of sums don't work for you to show it's equal to 0. We'll come back to this one. All right. So what are the reasons to expect non-vanishing? One of them is this conjecture due to Chola in 1965. This is not a paper, by the way. It's a book by Chola. He claims that Dirichlet L functions associated with quadratic Dirichlet characters do not vanish, not just at 1/2, but on this entire line segment 0 to 1. And this is still open. And it is believed that it is expected that this is also true for other characters, also primitive Dirichlet characters, and also for other L functions. All right. Okay. However, there is a result due to Lee, which says the opposite. It says that Chola's conjecture is false if you look at L functions over rational function fields, and there are infinite number of examples. However, the number of examples, counterexamples, compared to the whole size of the family is negligible. It is taught that it's negligible. So on the other hand, we have positive results due to Özlük and Snyder, which says that almost 94% of these characters are not going to vanish. Of course, this result is assuming the generalized Riemann hypothesis that the zeros are already on 1/2. So you can get this result only with GRH. On the other hand, 1 year later, sound showed without assuming GRH that 87.5% of them are actually non-vanishing. So that's quite a big percentage. And he is using uh, modified moments of L functions, moments with weights, basically. And Öztürk and Snyder, I think they're using uh, a different method I'm going to talk about. All right. So another supporting uh, fact for non-vanishing is Katzerner conjectures. So this is a summary of this one. So they say, this is by, I'm quoting from their own paper, by the way. So if you take a single L function, and if you look at the distribution of their zeros along one half or wherever they are in the critical strip, then you will see that they are not the randomly distributed. They have the same statistical distribution as certain classes of matrices, in this case, Hermitian matrices, random matrices. So the eigenvalue distribution of matrices resembles or matches the distribution of zeros of L functions. And this is for a single L function. You can show that. However, the disadvantage of this is that there are several different subgroups of these matrices, and then you cannot distinguish exactly which matrix family you're talking about if you use high zeros of L functions. But if you concentrate on the zeros which are very close to S equals 1/2, which are called the low-lying zeros, then for certain nice families, you can find the corresponding family of matrices. And because this is known already, I mean, the distribution of eigenvalues of matrices are already known because it was studied before to answer some questions in physics. So you can basically cheat from those answers to get an answers or ideas about the distribution of zeros of L functions. Okay. So Katz and Sarnak are looking at function field analogs of functions and also number field L functions. For function fields, they can say what the reason is for the source of the symmetry, but for number fields, it's not known yet what the reason is. So if you have a function field analog of your L function over number fields, then you can get an idea at least about what to expect. All right, so what are they exactly looking at is this. So you take a family of L functions, let's say, or family of whatever you want to say. You take a family and then you order the family by the so-called conductor analytic conductors up to a certain point. And now for a single L function, let's say f, you look at the zeros which are close to zero by using a very fast decaying Schwarzschild function. So as you can see, we have a very smooth function, and this is concentrated around zero because it will decay very fast. So this is in some sense counting zeros near zero for this single L function. But because there's a finite number of zeros only, you have to average all of these over the family and then look at the ratio of this versus the size of the family and see what happens when q tends to infinity. So is there a limit for this? And the point and the purpose is to show that when you take the limit as q tends to infinity, you will end up with an integral like which shows the distribution of zeros, where this is the density function, and this is supposed to be matching Here's the magic. This is supposed to be matching the corresponding densities in some family of matrices. And if you can do this, in some sense, you are confirming Kac-Sarnak conjecture for this family. Okay, but the problem is generally nobody was able to show this for arbitrary test functions. These are called the test functions that you're using phi. Okay, all the results assume that the Fourier transforms of these test functions are supported, compactly supported. So, okay, the conjecture itself is assuming that there's no restriction on the test functions. So, you can only confirm it with compactly supported functions. All right. So now I would like to tell how you get a non-vanishing result using this result. If you get a result for one level density, then you can also get for free a non-vanishing result as long as your result for one level density is strong enough, and you will understand what I mean. So this is the quantity I'm looking at, the number of f for which this function is not zero, divided by the size of the family. What's the percentage here? As q tends to infinity. Okay, so basically from the whole family, from sorry, 100%, you subtract this guy where the order of vanishing is more than equal to one, at least one. So at least you have a zero of order one. Okay. Then definitely you can replace this one by m, and you will get an inequality of this form. And now this sum over here is greater than or equal to this sum, which is almost looking like our density one level density, except I should not have zero here, but scaled zero over here inside. And all these inequalities I wrote are true if you choose your test function so that it has a value one at zero and greater than or equal to zero. So finally, you get you add more zeros, basically zeros which may not be at the central point 1/2. You add those points, then you will get this result, which is the density we have. So now, if you take the limit of both sides, you get a lower bound for this quantity. That's how you can use the information about the one level density to get a non-vanishing result. So if this is good, then you will get a nice proportion. So that's what I was saying. So I just for you to compare what's going on. Because I was working on cubic L functions associated with cubic families, I wanted to compare them to quadratic case. So as I told you, if your the Fourier transform of your test function is supported on this compact interval, then for cubic families or higher degree characters, you will get a unitary family. For unitary family, this is the proportion you can get. So the larger support you can get here, the better proportion you're going to get. And for symplectic family, as you can see, this is definitely much larger than this one. And this has something to do with the behavior of the corresponding matrix families, basically. Symplectic versus unitary family. Okay. So the left-hand side is what you get as the well, you're supposed to get as the end of one level density, and then by this theorem, it turns out to be equal to this guy. And so these are the important families that show up generally for matrices, orthogonal family, and even odd versions, symplectic family, and unitary family. and these are the corresponding densities. The point here that I wanted to show you here is that if, let's say, your Fourier transform appears on the side, if this has a support which is small, smaller than, let's say, minus 1, 1, then these three functions will have exactly the same value in that interval. So you won't be able to distinguish these guys, in fact, these guys, except the unitary one. Therefore, it's very important to go beyond the interval minus 1 and 1. And most of the time, it's very hard to go beyond that interval. For most of the results in literature, it's very, very difficult to go beyond that range. Okay, now the second method to show a non-vanishing result, as I told you, is using moments of L functions. But assume that these are the values of your L function at 1/2. You have, let's say, infinitely many different L functions, and you want to know which of these guys are non-zero at 1/2. So if, by the way, as I told you, the value of 1/2 is very complicated. You cannot directly see what the value of the function is, so you cannot tell exactly what's going on. It's like counting primes, basically. Um, so if you want to count the number of non-vanishing guys over here, you can use a very simple inequality, Cauchy-Schwarz inequality or Hölder's inequality to get this result. So the sum of the absolute values of these guys is less output to this one. And if you divide both sides by n, you're going to see that the proportion of non-vanishing for this sequence is given by, okay, lower bounded by this quotient. For example, if you take all the numbers equal to 1, right, this sum is going to be n, and this sum is going to be n. They will cancel each other. You will get 100% non-vanishing. But if these guys are like alternating series, like -1 plus 1 -1 plus 1, this guy will be 0 or 1 in absolute value. This sum will be n. So you're looking at basically almost 0% non-vanishing, even though all of them are non-zero. Okay. So in some sense, if there's a lot of cancellation, this won't give you a good result, obviously. But for L functions, unfortunately, because you cannot tell what their values are, this is kind of the only way, or one of the only few ways one can use for non-vanishing. Okay, so to get an idea about this, what you need is to give a lower bound for the top and an upper bound for the denominator. Evet. I have 5 to 6 minutes, I guess. Doğru mu?
No, you have more. It's 5:41. You have
Okay.
like 10 minutes.
Okay. Just tell me to stop when you cannot bear anymore. Okay. So now, if we take the sequence as the values of our L functions, let's say we have an infinite family of L functions, we're going to get, as I told you, this. So the denominator over here is called, for example, the second moment. And this is called the first moment squared. Okay, you need a lower bound for this and an upper bound for this to be able to say something about proportion. Okay, and that's where the story begins, basically. Okay, sometimes, as I told you, you can use Selberg's idea. For example, I mean, when do you use it? Exactly when the denominator is too large compared to the numerator. Okay, to get rid of that effect, I mean, the nuanced, basically, if you square something large, right, it will get even larger. So to get rid of that effect, you can try to modify, choose weights that will somehow cancel their effect, right? So if you choose the modifiers, let's say like 1 over this guy, so you're looking at the sum like Q over Q in some sense. So now they're balanced, you can say something. So that's the idea of using modifiers or weights, what it's called. Uh, and that's what Selberg did for the Riemann zeta function. Okay. But using modifiers is definitely not very easy, but you have to use it sometimes. All right. Okay, from here on, basically, I just introduced the methods. Of course, after that, everything you do is use all the available techniques, right? In analytic number theory or any area you can find to be able to say something about these things. Okay, that's what. All right, now I want to show you. Okay, let me go to the previous page. So basically, when you start to say something. For example, let's say you want to look at the second moment here. One method is to open up this one, write this L times its conjugate. You can write the square of this. The conjugate, what is the value of N of 1/2? You don't have it. So what are you going to plug in here, right? You don't have the value. So what do you do then? So what we do is generally, this is the value, actual value, but this doesn't work in generally. What you do is you use what is called the approximate function equation. So this is one example that I used, for example, in my research. Uh, so these are cubic characters, and the value of the function at 1/2 is given as two infinite sums. These are infinite sums, but you have a smooth, very fast decaying function. So these are like finite sums. Basically, when this input becomes around size 1, let's say these are around 1, after that it will decay very fast. So this is, for example, this first sum is like norm A going all the way up to Y only in some sense. So these are like finite sums basically. Uh, so you can replace this guy by these finite sums, put them back above here, and then try to see what you can say with them. And that will cost probably 30 to 50 or 100 pages. All right. So that's what I wanted to mention. That's how you begin the game, basically. Okay, quickly mentioning the results, some of the results, of course, there are millions of results on this area. Kind of a dangerous zone if you want to get in the game because it's like there are giants here. So anyway, so as I mentioned before, we have this percentage for non-vanishing. For quadratic characters, this is assuming GRH, and the Fourier support, as you can see, is between -2 to, and these two are related, as I told you. This is obtained exactly by subtracting from 1 minus 1 over 2 times the square of this number. This will give you this number. Okay, so the larger the support, if you put infinite, in other words, you will get 100%. And Sandro Rajan, he gets this guy. And then here's another result that I mentioned at the beginning of my talk. Due to Ivanich and Sarnak, they look at this lower bound. As you can see, this is not zero. This is a little larger than zero. So they are trying to show that these guys are lower bounded by this quantity. And as k tends to infinity over this family of Hecke forms, they get this lower bound. And this is a very, very good result. And then what they say is if you can go past beyond this point, 1/2, if you can get anything larger than 1/2, you're going to show that there are no Ziegler zeros. So this is how this result of non-vanishing, in some sense non-vanishing, is related to Ziegler zeros. And also Kowalski-Michel, and they get another result for different family. Uh, okay. So let me mention now some other results which are related to cubic characters. That's the family I started to work with, by the way, initially in my PhD and then later on recently over the years. Okay, so for cubic family, there's this result. So you can look at cubic characters over integers, the usual Dirichlet characters, or you can look at over this number field, where the third root of unity is adjoint. Okay, and if you look at the cubic characters, there's a whole family of characters, and there's a subfamily of which is thin inside that family. So that's why I wrote thin family. And for this family, these results, as you can see, have support within -1 open interval, so that they cannot get a non-vanishing result from this one, unfortunately, as I said. And again, with GRH, they went all the way up to -1, still not enough for a positive proportion. And if you use moments, my advisor, PhD advisor, he got the result again for the tin family. I was trying to write tin, but I wrote think. Okay, and then he showed that in this tin subfamily, there are infinite many L functions which are non-vanishing, but as you can see, the size of the family itself is X, and this is little o of X. Therefore, you cannot show a positive proportion of non-vanishing again using momentum. Bayer and Young, they also get a similar result. Again, we have an infinite number. But these results at the bottom are unconditional, so they don't require GRH. Finally, we have an infinite number of zeros obtained over function fields, and after that, they were able to obtain, even though the years don't show that, they obtained for non-communal case a positive proportion for the same family, uh, 2020. All right, finally, we are about to finish. So what we did with Chantal in 2021, we took uh, cubic characters over the number field, which is what I did in my PhD anyway. And then we assumed GRH. For the tin family, we were able to obtain this proportion only, 2 over 13, using the one level density. And I mean, our purpose was not non-vanishing. We were trying to look at one level density, Katsanak basically, and we were able to go beyond -1. Therefore, we were able to get a positive proportion of non-vanishing. After that, Hamza and I looked at the full family, which is much harder than tin family, and we assumed GRH and we use modified moments, and we get a positive proportion. And but as you can see, the proportion is like is almost zero, uh, because of the difficulty of or the method that is used. This is what you can get generally. Okay, finally, I looked at the full family without GRH, and I was able to show there are infinite number of non-vanishings in this family. Okay, very recently, I think within this end of the last year, David and four more other people, they were looking at the tin family again using a different modifier, the method that Sandra Rajan used before for quadratic family, and they were able to get, without GRH, this proportion, 1 over 7, which is still lower than what we got with Chantal. 213 is larger than this number, but again, this is, as I said, this is no GRH involved here. Okay. Do I have any time left, or I have just a couple of slides left, but I can stop here if you want.
You can show them.
So I
Yeah,
just want to, I mean, the
have a few
relate,
minutes.
so
Of course.
just this one. So what I want to say again, for the one level density, we take the zeros, put it in a test function. This is for a single L function. And then we use a smoothing here. We look at the infinite family with a smoothing. And then basically average over the L function, divide by the size of the family. So this is called the smoothed version of one level density. Many people use this one. You get slightly better results with this. Then the game, so what I want to show for this part, this is for a single L function. And when you write the formula for this, which is called the explicit formula, the very first term that you see here already tells you this family behaves like the unitary matrices, or even for a single L function. And the rest is to get rid of these giant guys, and these guys determine the fate of the Fourier transform, basically, these guys. Anyway, and then use lots of other techniques, of course, to be able to get results. And for the other modified moments, with Hamza, we got this asymptotic formula, in some sense, an asymptotic formula using this is the modifier. For the first moment, this is called the first moment, you need either a lower bound, as I told you, or an exact formula. And if you take the limit of this one, it will give you a lower bound in the limit for this one. And for for here, as you can see in our paper, we compute the moments, modified moments for any k though, in this case. So it's not just for 2, this is for any k larger than 0. A real number, sorry, not integers. So to be able to get this one, and the proportion, as I said, is terribly small, but it's positive proportion anyway. Uh, this this second one requires GRH. The first one we were able to get without any GRH. So this is unconditional result. And finally, what I want to mention for the general, so for example, if you have square of an L function, as I said, you can write it as a product of L function with its conjugate. But if you have, let's say, a general real number, what you can do is apply e to the power log to that function, and then you're going to be dealing with the logarithm of an L function. So this is an upper bound you can use for that, and then you have to exponentiate both sides to be able to multiply both sides by k and then exponentiate both sides, and then good luck. Then you will have 50 pages coming up. Okay, these are the modifiers that one uses. As I said, these are supposed to behave like the inverse of the L function that you have so that they will cancel each other. So let me go back very quickly. To be able to get positive proportion of non-vanishing, you will need the size of this and the size of this the same. So this is the size of our family x log x, and this is f of x. When they are the same, then you can get positive proportion. Okay, normally if you don't apply this one, you will get a larger power here, and then you won't be able to get positive proportion. That's what happened to me in my last paper. This is unconditional, as I said, for the full family. I get an asymptotic formula for the first moment. For the second moment, I get an upper bound. As you can see, this is larger than 1. So the size is x log x. This is larger than 1. So you won't get positive proportion for sure, but you will get an infinite number. In other words, you will get, compared to the size of x, you will get this many L functions which are not vanishing. Okay, that's supposed to be the end of it.
Thank
Thank you.
you. Let's thank the speaker.
All right.
Um, Sorry. Now, are there any questions?
All right. They must be sleeping. Okay. Thanks for listening until the end.
Thank you,
Appreciate it.
Ahmet.
Merhaba İlhan Hocam.
Merhaba.
Evet, şiiri stop ediyorum o zaman bu şeyi, paylaşımı.
Okay.
Thank you.
Ahmet, so this is a record. We had uh, more than
Oh,
35 participants in your seminar.
oh my God, 30 people has been tortured, unfortunately. Sorry about that.